I'm Ron Sicker. I'm the project manager for an experiment known as the Advanced Colloid Experiment at the NASA Glenn Research Center. And we just completed our first experiment. It was a successful experiment with my colleague here at Procter & Gamble, principal scientist Matt Lynch, and my project scientist Bill Meyer from the NASA Glenn Research Center. And we thought that we would come and have a debrief and talk about the mission, but also it got some curiosity going. Being an engineer, I got thinking on how scientists and engineers interact to do these experiments. So with my engineering curiosity, I asked the experts how to remove some very difficult coffee stains from my carpet, and they said, use Dawn. And I was looking at Dawn, and I noticed how it can also be used to take the crude oil off of a baby duckling. So, Matt, thanks for that, and maybe I'll put you up to explain some of the spin-offs and other uses for Dawn.
Very good. It's great for cleaning sinks too, I understand.
Cleaning sinks?
Cleaning
Okay.
sinks? Yes, cleaning clogs. Very good stuff. Yeah.
And there's lots of ingredients in a product like this, or?
Yes, quite a few. Surfactants, solvents, water, things like that. Sometimes some electrolytes. And you got to pack it all really tight together so it fits in a small bottle and keep it nice and clear like that. So it's a bit of a trick.
Yeah.
A bit of a trick to make it work.
So as I was looking around the house, I found all kind of other things that might pique my curiosity.
Yeah. Oh boy. All right.
Another one was the amazing gel where the particles never sink.
Yes. Of course, now it's very relevant to our ACE experiment, right?
Yeah.
Because, so what you have are some particles that are suspended in the fluid being the surfactant system,
Yep.
right? And normally, just like maybe like a beach ball or something like that, it's a density difference between the fluid and the little particle. Like a beach ball would like to kind of rise up
Yep.
to the top. So what one has to do is figure out a clever way to kind of keep that from rising, or sometimes keep it from sinking in other products too. And at the same time, when I push this little button, it's got to be able to kind of come out as a nice material, nice easy flowing material. So the trick is how to make all that work. And one of the interesting things about this is when you shake it, you kind of notice it kind of vibrates and jiggles a little bit.
Yep.
And so what people do is they create what they call a yield stress fluid. And that's the idea of putting in, for example, in this case, a polymer. And the polymer kind of weaves itself together into like a net or a little mesh. And that mesh itself is sufficient to hold all the particles in place. But if you push too hard on the net breaks and everything flows just like water. The ACE experiments are similar to that. So we use little particles, little colloids, smaller than you can ever see by your eye, like the size of a pin. We're going to put those in there, and we're going to try to assemble them in ways that provide the same functionality. It's a net. The net holds all the particles in place, and then be able to break that net up into small pieces when you push on that lever.
So when we go to space, you can see these events happen on a time scale of 10,000, 100,000 times longer than it might happen on Earth. And that's the reason that we're all in the same business. Procter & Gamble is in the business of overcoming gravity in some of their products. That's why a properly designed product doesn't sink or separate.
Yeah.
But we go to space to overcome gravity. Of course, we used rockets and we use the space station. But we all share that overlap of spin-offs and using overcoming gravity to do our mission.
Well, and from a basic science point of view, if I want to understand how to design a system like this, one of the challenges is that gravity adds a lot of complexity into the whole understanding of the problem. So as things begin to settle, they push fluid around, you get hydrodynamic components, that pushes other particles. If I want to understand the basic physics around this kind of reorientation and resedimentation of all of the different particulates, these little colloids in there, then I have to take gravity out of that equation. So that's what affords us a really neat opportunity in the zero-G environment.
So I remember you explaining this back in 2009. I think you were at a microgravity competition. We were actually going to fly an experiment in space.
Yeah.
And it ultimately came into a whole set of experiments you're flying in space right now. And from what I understand, you're getting not only pleasant results, but pleasant surprises.
Yeah.
Can you tell us some of those?
Yeah. Well, okay. So if I was to take a product that we suspend all these colloids in to make it, they begin to move in time, just like in the same way, just with a little bit of heat. There's what we call Brownian motion. Things move and they jiggle, and those structures, those little nets, begin to change. They'll change in time, and to the point where they don't function properly anymore. And for us, it is understood that it becomes a more complex problem when those little particles, those little colloids, are different than each other, a little bit different in nature, a little bit different in size, say, for example. Very typical for what we formulate and make with, but not really well studied in literature. Most people want to be very clean, very pure on things. So we're making kind of a middle step, and what we find is that when we put these kind of impurities in there, there's this polydispersity of the small materials, the physics looks a little different than is typically noted. All the materials move around at different rates. Small things and big things do different kinds of things, leads to lots of different dynamics. For us, that dynamics leads into how long these little balls stay suspended.
So I remember when you were talking in this 2009 presentation, the people were really excited because you were talking about what would happen if you understood the products better, understood the stabilizers better. And what was a surprise for me was that the stabilizer is a major part of the product. And what it is it's something that actually doesn't interfere with the product and allows it to be itself, but without it.
Right. Well, that's what you're trying to do. So it's something that allows you to then go ahead and make the product efficacious in some way. So, for example, in a shampoo, that might be little silicone oils that get on your hair that make the hair feel good and have a chance to comb it, dry it faster, comb it better, things like that. You can't do that sort of thing often without stabilizing the product appropriately. So it in and of itself, often it's supposed to be benign. It's supposed to be there. It helps you make the product, makes the product work. In and of itself, often doesn't have a lot of function. It can, but it's a necessary component to make a lot of these materials, a lot of these products work properly.
So I also heard you say that if you get a good stabilizer and you really understand it, which is something that's really hard to do at the moment, and why you're doing the space experiments, then you would be able to make much smaller packages, and you'd have, other
conceptually, yeah. I mean, a lot of things are possible. I mean, you can imagine suspending different sorts of things that you can't do now. Different sorts of actives, different sorts of materials of interest. Right now, they may be too heavy for a net, so you just punch through. But those things become more possible by having things that you understand how to do. And frankly, from a research and development perspective, I want to make something like this, get it out to people to help them, so they don't get germs and things on their hands. And you want to make this product as quick as possible. If you often formulate in the dark, you make things in the dark in a sense, a proverbial sense in the dark, where you're going to go out and you're just going to mix and match, it takes a long time to make that work. If you have some directed design, you know what you kind of need, you know something about the composition of things, the attractive nature of particles, the sizes and all how that works, then you can make it very quick. And that helps everybody. It helps the company, it helps the consumers. So if you think about something like this, it seems somewhat benign. It's a hand sanitizer, has a lot of great function for people, and P&G products touch about 4.5 billion people on the planet each day, about 2/3 of the entire population. So our ability to help people's lives, come back and make things that help people's lives is just great for everybody.
And you had said that if you use textbook-sized particles, which are all the same size, then you can model it, you can use computers to understand and predict, but that's not what you produce. Textbook particles don't exist.
That's right, yeah. And actually, part of the surprise that we're finding in the experiments, well, I say surprise, we're finding in the experiments is a little bit about how that physics differs. We can see that in a microscopic sense. We can see that on a bulk sense with some of the cases work as well. But we've kind of known that for a long time in the formulation work, so where you go ahead and you change the nature of the materials that you're trying to making as your suspending aids, and those dynamics change quite a bit. Something that may be very good for several months or a year, mix things up in a slightly different way with different kinds of materials, different size materials, all of a sudden leaves a couple weeks. And how do you predict that? How do you understand that? How do you know that? That's just something that's right now beyond our ability to deal with.